Let the universal set S have 96 elements. A and B are subsets of S. Set A contains 63 elements and set B contains 16 elements. If the total number of elements in either A or B is 70, how many elements are in B but not in A? This is actually a rather challenging problem. But when I see a challenging set problem, I like to visualize it, so I'm going to start by drawing a Venn diagram. On the outside, I have the rectangle that designates the universal set S. And I'm told that the number of elements in set S is actually 96. So I know that there's 96 elements in the rectangle. Now within that rectangle, there are two subsets. Set A, which I'm going to designate with a pink circle, and set B, which I'll designate with a green circle. Now what do I know about sets A and B? Well, set A has 63 elements, so I'm going to write down that the number of elements in set A is 63. We're also told that set B contains 16 elements, and so I'm going to write down that the number of elements in set B is 16. What else are we told? What else can I write down from this problem? Well, I'm told that the total number of elements in either A or B is 70. Now the key word here is or, and when you combine or with set theory, you're usually talking about the union. So when I'm talking about the number of elements that lie in either A or B, what I'm really saying is that the number of elements in the union, A union B, is 70. Beautiful. So now we're to the most important part, which is identifying what are we actually trying to solve. The last sentence, or actually the last question, is what we're looking for. How many elements are in B, but not in A? Let's look at our Venn diagram. Where is the set of elements that lie in B, but not in A? Do you see it's this portion right here in our Venn diagram? It's the portion inside of B, or in the green space, but not in the pink circle, right? This is the portion that we're looking for. We're trying to discover how many elements lie there. So what's our strategy? Well, it would be helpful to know how many elements are in the intersection, and that would be a good place to start. Why is that? Because we already know how many elements are in B total. So if we can figure out how many are in that little pink-green overlap, or the intersection, then we'll be able to subtract and get the number that lie outside in just the green portion. So how can we do that? Well, we can either look at it and just go through the math, or we can use our cardinality rule to help us. Recall we have this rule that says that the number of elements in the intersection is equal to taking the number of elements in the first set plus the number of elements in the second set, and then subtract the number of elements in the union. Or in other words, the union actually consists of adding up all the elements in both of the sets and then subtracting off the intersection. But another way to view it is this way. The number of elements in the intersection is the number of elements in A plus the number of elements in B minus the union. Well, that's going to help me because I know that the number of elements in A is 63. I know that the number of elements in B is 16. And I know that the union has 70. So that means the number of elements in my intersection is just 89 minus 70. Excuse me, I did that math wrong. That's actually, erase that. That's 79 minus 70, or simply 9. So the number of elements in our intersection is actually 9. And we're almost done. The last step, Because I know that the entire green circle has 16 elements, if I subtract off those 9 elements in the intersection, that gives me the leftover part that is on the outside, meaning the leftover part in the green set that is not included in the pink set. We have a total of 7 elements that fall in B but not in A. And if I want to write it in notation, that would be the number of elements that fall in B intersecting A complement. So they're not in A. That was a little challenging. If you do have any questions, don't hesitate to reach out.